I'm Rajneesh. I'm co-founder of a couple of companies, slightly diverse set of companies, I would say. Right? Both of these work in different areas. I'll give a quick background about the two of them. I think I spoke about Bulian AI the last time we met in person, right? I'll add another one to that list today. I hope to keep the list of companies to two. I hope it doesn't grow too much. But yeah, so Boolean AI is basically a low-code, synthetic data platform. Essentially, what we do is we enable companies to deploy deep learning models, which can help them generate synthetic data, right? And of course, the use cases of synthetic data are vast, right? So you can think of use cases in cloud migration, you can think of use cases in MLOps, DevOps, provisioning, and general purpose innovation. Our target area here is specifically to increase efficacy of machine learning models, right? Specifically in domains where you don't have a lot of data, or in particular where you have a lot of regulatory compliance around what kind of data you can use and what kind of things you can do with that data, right? So specifically in areas like banking and pharmaceutical, we are finding a lot of applications there, and we are working with a few consulting clients as of now. So companies like Accenture, KPMG, where we are kind of slowly developing certain POCs with them, right? Uh, so this is like a very niche AI-based system for now. And the other company that I've just co-founded with another one of my colleague is Finnex, right? And this is specifically directed towards making use of alternate data APIs for fintechs, right? So if you're in fintech, you probably know about things like credit data sets and a lot of things that come from credit bureaus and so on, right? Banking history as well. But we are here kind of trying to make use of alternate data, right? So think of all the data that is collected via smartphones, right? Your location, your apps, etc., etc. So we are focusing here on those few alternate data APIs, and this is specifically geared towards geographies like India, Middle East, where you're going to see a big fintech boom in a few coming few years, right? So, right, that's a bit of an overview. If any of these interest you, feel free to reach out. I can talk more and probably give a demo or two if you're interested. Okay, so now I'll quickly move on to the competition, right? So competition is basically Mars spectrometry, gas chromatography. So pardon my pronunciation. I'm not a chemical expert, or I'm not an expert in this domain, right? And again, one of the things I also wanted to highlight with this competition is you can probably do well in a lot of data science stuff, even if you're not a domain expert, right? So for example, I've never seen or worked in this kind of data set before, but I still was able to do well because I was able to look at the data in a certain way and all of that, right? Uh, so yeah, one of the points I almost always emphasize is you don't really need to be a domain expert. Of course, if you are a domain expert, it adds a lot of value on top of what you can do with data science. But even if you're not a domain expert, you can still achieve a lot if you're a good data scientist, right? So yeah, case in point is this competition where I'm not a domain expert, so but I still did reasonably well, right? So what was the competition about, right? So quick overview. This competition is basically was hosted by NASA, and it was hosted on DrivenData.org, which is a Kaggle-like platform. A lot of Kagglers move, to and fro between competing on Kaggle and competing on Driven Data, right? Uh, uh, and the competition is basically hosted by NASA. And the idea is, so NASA has this Mars rovers that they've sent to Mars, right? And these rovers are essentially collecting a lot of data, right, around soil, chemical composition, the looking for water on Mars and stuff of that kind, right? So atmospheric measurements and so on. And the key question that they're trying to ask is, did Masa ever have conditions that could have supported life, right? And how do you gauge, or how do you come to an answer of this? Is by looking at chemical composition of soil, or looking for water underneath the layers and so on, right? This competition was specifically around looking at soil samples, and then what kind of molecules were found in those soil samples, right? And then creating a model to predict these soil samples given a set of input data set, correct? And again, we are looking at chemical signatures that could indicate habitability or potentially even signs of microbial life activity. And in this competition, the task was to build a model to automatically analyze mass spectrometry data. And again, I'll quickly talk about what is this mass spectrometry data in the next slide, right? But again, I'll not go into the details of it. I'm not a domain expert. I'll touch it from a very high level 360, 3000 feet view. So yeah, we look at mass spectrometry data of geological samples, and then we try to understand what are the chemical compounds, specifically organic chemical compounds that are present in this, and then we see whether we can build a machine learning model center that could take in a sample, or let's say that could take in a mass spectrometry inputs, and then predict what kind of samples we can expect to find in this particular data set, right, or sample. I'll take a quick pause if anybody has questions here. And also let me know if I'm going too fast, too slow. Okay, no questions means either people are not understanding or everything is too clear. Okay, I'll assume it's clear. All right. So quickly talking about the gas chromatography mass spectrometry, right? So what exactly this big thing means? So it's basically a chemical procedure to generate some kind of data set, right? And you can imagine you have certain set of inputs. Let's say those inputs are, samples, soil samples. And what happens is you essentially vaporize these soil samples into gas, right? So you basically heat them up at very high temperatures, and that vaporizes whatever you're trying to vaporize, right? Most likely it's a soil sample. And then what you do is you basically pass this gaseous form of your sample through various stages, right? So one of the stages you pass it through a propeller inert gas like helium or hydrogen or nitrogen, right? And then as they pass through these columns, like they call it, these gases are then ionized, right? And then they essentially separate out into their respective compounds, right, based on their mass to charge ratios, right? So think of it as you have a solid, you vaporize it, you convert it into gas, you then pass it through certain set of chemical compositions, mostly inert gases, helium, hydrogen, etc. And then you are able to separate out various types of compounds from that process itself, right? And at the end, what you essentially get is something like a chromatogram, which you see here, right? So in the next slide, I'll show you what the entries of that chromatogram are, right? But essentially, these are things or chemical compounds in your sample separated by various separated across various elements, right? So you could have certain kind of, let's say, certain kind of nitrogen compound separated in a particular way. You could have certain kind of carbon compound separated in a particular way, right? And so on and so forth. There are like 20-25 odd things that you are interested in, right? And that's what comes out of this entire mass spectrometry process, right? Very like highly domain specific. I didn't understand 100% what happens inside the spectrometry process, but this is what I understood at a very high level, right? You heat stuff up, you convert it into gas, you ionize it, and then you essentially measure what these ions look like, right? In the form of a table data, essentially. Okay. Okay. Now, this is what the input data looks like, right? And in the last slide, I talked about the output or the mass spectrometry data, right? So this is a snapshot of one sample, right? So if you see, there are three columns here. You have time. Time is in seconds, of course. Then mass to charge ratio, and then intensity, right? So if you see, you have like, and again, since these are like chemical reactions that are happening, right? Most of these things, or a lot of these things, will happen simultaneously, right? But if you see here, the value of time is constant for a particular snapshot of this sample, right? That basically means a lot of stuff happened simultaneously at this particular time period, right? So again, chemical reactions, some of the chemical reactions happen almost simultaneously, right? Not all of them will happen simultaneously. You'll see at like different timestamps as well. But this, the objective of showing this particular view was to was to communicate that you will have a lot of stuff happening simultaneously as well, right? So you have one value of time, varying value of mass, and varying value of intensity, right? And this is just like top 3-4 rows of a particular sample, right? Now you can look at this data set in two ways. One is basically you can plot intensity and mass, forget about the time aspect of the entire analysis, right? And what you'll see is you'll see various peaks, right? So you'll see how the mass varies, or let's say how the intensity varies across different values of mass, right? So you can see what are the various values of peak intensity for different mass values, right? That's one view, which is called the histogram view of things. The second view is called the mass spectra over time. So here what you do is you basically pick a value of mass. So let's say I pick the first value, which is 45.2, and then you can plot all the values of intensity and time across time for that particular value of mass, right? So what you will have essentially here is a series, a time series sort of thing, but time series, different time series for different values of mass, right? And again, time series, the x-axis is time, the y value will be the intensity value, right? So this is another view of the same thing. Of course, you can probably imagine the second view is a little bit more richer in the sense that we are looking at different mass, different series for different mass values, right? So this is probably a little bit more richer and granular than the simple histogram, which is probably a global view of sorts, right? We will of course make use of both of them when we come to the modeling part, right? I'll take a quick pause here, see if I'm clear or clear, or if there is any questions on data, how the data looks like.
Yeah, it's
Okay.
quite clear, but maybe you will touch upon that later on in your talk. How do you deal with the time aspect? So sometimes it's instantaneous, but some of the times the chemical reaction can take time. So do you have a time series model or something?
Right. Yeah, we will come to that. So I'll basically talk about how to create features for each of these views, so to speak. Okay. So all right. So we come to that question directly actually in the next slide, right? So how do we create features, right? So there are two types of features that I created specifically for this. This is the first one, which is essentially trying to create a spectrogram, right? So if you've ever worked with, let's say, audio data, right? So audio data, you basically can create a spectrogram of sorts using audio data, right? So I worked on a bunch of audio data competitions or signal data competitions in the past, and I thought, why not take that inspiration and try and plot this entire time series as as multiple time series as a spectrogram of sorts, right? So, and essentially this involves very intensive cleaning and aggregation process, right? So and at the end, what you basically want to see at the end is something like this, right? So you have a picture, and the x-axis here is basically, I think, the mass values, right? And the y-axis is the time value, and then you basically do some kind of aggregation for each of those intersections, right? So mass cross the timestamp, right? And again, we will see what I've done here, right? So the first step here is, of course, cleanup, right? So you look at the mass values, you do some kind of domain specific cleaning. So things like you round up the mass value to the nearest decimal, right? You drop helium and some other inert gases. So at the start, I said there are certain inert gases that are injected just for the just because that's how the process or the entire analysis is conducted. So anytime you see helium or at least the atomic weight of helium appearing in your table, you drop those rows essentially, right? And then we were also told that most of the compounds that we are going to find, they're going to come from the range of values, mg values less than 350, right? So there was this mg column. We essentially dropped everything less than 350. And again, the reason why we dropped it is so one is domain insights, right? The second is the data size would become quite huge if we did not, right? So you can imagine what I showed in the earlier slide was just a small snapshot. You're looking at multiple samples and a lot of like lengthy time series data sets, right? So you want to kind of reduce that dimension as much as you can, and best dimension reduction techniques are probably dropping certain values if you have some domain insights, right? So this was another domain insight that was essentially told to us by the organizers, that you can drop some of these less than 350 values, right? So that was a bit of cleaning up. Then what we want to do is we basically want to come up with some kind of aggregates for intensity, right? And what we did is we basically created mean and max intensity by time and the mass values that we constructed earlier, right? So you can imagine for every rounded value of mass and every value of time, we have like one value of intensity, right? So I think this answers the previous question a little bit. as in how do we come up with like or what kind of processing we do to come up with features, right? So in this case, it was simply aggregating across time and mass, right, and computing one number. We did a couple of experiments, one with mean and another one with max, right? They were fairly close to each other. Then okay, then basically what we did is we did some normalizations, right? So within a particular observation, we want to kind of scale or rather remove background intensities, right? So this, think of this as something like a G normalization of sorts, where we subtracted the minimum value from all the observations, right? Once we have the minimum value subtracted, we wanted to scale everything to a 0.0 to 1 scale, right? And again, the reason we want to scale everything to 0 to 1 is because our ultimate goal is to create a spectrogram, right? And again, think of this as when you're working with images, you want to normalize everything by dividing the pixel values with 255, right? So this is something very similar to that, right? So scaling everything to 0 to 1 range by doing a min max scale. And at this point, we still have a lot of values of time, right? So time is like a lot of discrete values like 0.004, 0.003, right? And so on and so forth, right? So a lot of different values. We cannot work with those many values, right? What we want to see is what is the average behavior, let's say, within a particular time bucket. So what we do is we divide time into certain buckets. Here we did a couple of experiments around, let's say, we divided into 0.25 second bucket and 0.5 second buckets. And again, within each time bucket, you want to again come up with some kind of average behavior, right? Or average statistic, right? That average statistic here is again mean or max intensity, right? So again, keep in mind we are doing aggregation twice. One we did at the start where we said we are going to do a mean max aggregation of intensity by time and rounded mass, right? But here we did not have time buckets. As soon as we got to time buckets, by choosing an appropriate bucket size, we again did a aggregation, right? So mean and max intensity calculation, right? And that essentially gave us, and again, you can decide how many buckets you want, right? We did like 2 or 3 different kind of buckets. So if you see here, like we have 101 cross 351, right? The first number is the time, the number of time buckets. The second is the number of mass values, right? So 351 is the mass number of distinct mass values that we're considering. 101 is the distinct values of time buckets we're considering, right? And for each of these 3 different configurations, we would get to something like this, right? Like a spectrogram. On the x-axis, you have the mass scale or the different values of mass. And again, we have rounded the mass at the start, right? So these are like 0, 1, 2, 3, 4 integer values essentially. And y-axis is essentially the what is the y value? The y value is a time scale, right? And the values that go into this are the average intensity values, right? So we want to see how the average intensity varies for each of these rounded mass values, right? Across time steps, right? Or time buckets, so to speak, right? Of course, you can probably argue, you can probably do a lot better if you take even finer buckets or create even finer buckets of time, right? So probably for somebody 0.25 is a very wide time bucket, right? And it probably is, right? But again, you have to keep in mind as soon as you go try and go very granular on the time scale, you increase the image size, right? And then that has implications of what kind of processing you can probably do down the line, right? You probably need a very powerful GPU, 48 GB or whatever, right? To even have reasonable batch sizes for your deep learning algorithms, right? So this is the first step. This is the first set of features that we created, essentially creating images out of the input spectrogram dataset. And the idea was to try and use pre-trained deep learning vision models like transformer models or CNN models, right, to train the model, right. Second is we also wanted to do some boosting models, or let's say regular tabular models, and that required us to take a different approach, right? That required us to basically work around peak identification features, right? So again, I'll quickly go back, right? So here, if you see, you have different peaks, right? In both the cases, right? Over time or the general histogram view, right? Now you can create a lot of features by identifying peaks in each of the cases, right? So if you're able to figure out, let's say, what the peak values are, where do the peak values occur, what is the next value closest to the peak, right, and so on and so forth, you can create like a number of features. Then you can have like one set of features for each sample, right? And that's what we focused on here. We wanted to use tabular models, so we did a lot of stuff around peak identification, time to peaks. There are a bunch of stuff like identifying the prominence of each of these peaks, height of the peaks to mass ratio, and so on and so forth, right? A bunch of features around peak identification and stuff around that peak. And of course, we also did a bunch of aggregations around, intensity. So min, max, mean, median, skewness, kurtosis across time and mass buckets, right? Again, the idea here is to create these tabular features and then try and use some kind of boosting models to try and predict whatever we are trying to predict, right? So two set of features, one for deep learning models, one for tabular models, right? I hope that also clarifies the earlier question. I'll take a pause here if there are
Yes.
questions.
So Rajneesh, a follow-up question from me. So you have two sets of features with different characteristics, one that are image-like, those are like tabular-like. So is it for doing two different model and compare, or do you know how to do a unified model for both?
Yes, yes. So we will do separate, right? But at the end, we'll also see a way to combine. How do you combine different predictions, right?
Okay, that's
Yeah.
exciting.
Okay. All right. Okay. So this is probably a very plain slide, right? So last slide we figured out we created a bunch of spectrograms, right? And again, one of the advice I generally give is if you're working on any, this kind of pipeline where you're creating images of out of your signals, right? You probably want to save these to your disk, right? Otherwise, what I've seen is like people they don't save these to disk. They have like a continuous running pipeline, batch pipeline of sorts. When they have this entire unified pipeline, something creating the input and then feeding that to the neural network, it becomes a very time intensive affair, right, so to speak. So my general advice is divide the pipeline. As soon as you have outputs of one part of the pipeline, save them to your computer or to your cloud, whatever, right? And then utilize the things that are saved in the later stages, right? Rather than having to do it all, while training the model itself, right? So we created these spectrograms, saved them to the disk, and then what you essentially want to do is you want to do k-folds, right? So five-fold kind of model validation. And here we created let's say a custom kind of pipeline, right? So this pipeline has 2D vision models, like a lot of transformer inspired models, right? So things like VIT and so on and so forth, and of course a little bit of ResNet like flavor as well in there, right? So around 16 deep learning models. But these deep learning models don't operate directly on the images. They do, but they also have the 1D LSTM component with it, right? So we pass the image to a 1D LSTM, we pass the image to the 2D backbones, whatever output we get, we concatenate, and then we do a multi-level predictions, right? So slightly unique architecture. Again, uh, this architecture is also inspired from one of the past Kaggle wins. Like 1 year ago, there was this competition called G2Net, where I used somewhat similar architecture, right? And it worked pretty well here as well, right? So anytime I see signal data, I generally go to this kind of architecture, right? So 2D backbones, 2D vision backbones, as well as 1D LSTM model in parallel, you concatenate. And of course, all of these are trained together, right? These are not separate models. These are trained together. And you can get like multi-level predictions at the end, right? So that's the vision model pipeline. This is not, I mean, we're saying this is not exactly pure vision. This is like vision, custom vision model, right, so to speak. And of course, the model pipeline for tabular, we created the features, right? We create the K folds, again, making sure the folds are exactly the same as the folds in vision models, right, or custom vision models. And then you of course train a bunch of these XGBoost, CATBoost, right, GBM, logistic regression, and so on. So 6 models in total, and then you get your predictions, right? Again, fairly straightforward. Then at the end, what we want to do is we want to combine all of these things together, right? And here we use something called greedy hill climbing weight optimization, right? So what you want to do is you have predictions coming out of each of them, right? And again, when we say predictions, we want to optimize certain set of weights on your validation set, right? And again, that's why we kept the validation sets same for both of these model sets, right? So whatever folds we created for deep learning models were kept same in the tabular models as well, right? Now, what we want to do here is we want to take those out of fold predictions, and we want to do some kind of greedy hill climbing via Optuna, right? So Optuna is like fairly exhaustive optimization library, and you can basically create a sort of objective function, right? Wherein you want to optimize a particular objective. I think the objective in this case was multi-label BCE loss, right? I guess binary cross entropy loss, right? Across all folds, across all labels rather, right? So you construct your objective, you construct your out of fold predictions, right? And the Optuna library will basically give you a set of weights that you should attach to each of the models, right? So for example, it might say give zero point 0.1 weight to this particular deep learning model, right? Give zero point 0.2 weight to this deep learning model, right? And of course, the weights might sum to one, right? So that's how we try and combine different models outputs, right? In an optimized way, right? Of course, you can argue why can't I simply average all of them? You can, but that might not be the optimal performance, right? As far as your combination is concerned, right? And again, think of these as like some of these might be heavily correlated amongst themselves, right? So some predictions might be heavily correlated. You don't want the same thing represented twice or even more than twice in your models, right? So this optimization will basically take care of that. It will try and assign higher weights to things that are unique to that particular output, right? And are of course good as well, right? And it will scale down the weights for things that the model can already see elsewhere in other models outputs, right? So we get to some sort of weighing scheme for each of these model outputs, and then we of course combine them, right? So the final rule could look something like zero point 0.1 times the outputs of XGBoost, 0.02 times the output of CatBoost, and so on and so forth, right? So things like a weighted average, right? And then once you have those weights, all you need to do is you simply need to go back to your average model predictions for each of them and apply the same weights to the actual test predictions, right? And yeah, and then you submit to the leaderboard, and then you get a particular rank. So yeah, that was that was it. Yeah, that was basically how you do like weight optimization or hill climbing optimization, right? And again, this was something that I hadn't tried for a long time. Doing ensemble weight optimization using Optuna. So this is something new that I did here. Of course, all the pre-processing was also new, but this was especially very exciting for me. Yeah, that's the talk, I think, about the competition. So feel free to ask your questions.